Hello my dear students, this is Akash SD and welcome to the ASD Physics classes students. I hope so you all are doing really great. So students, in this video we are going to learn about the Ohm's law, that means resistance, and how this resistance will change with the temperature. With that we will see how the semiconductor, insulator and all will behave with the temperature, and at the end of the video we will learn some basic things related to the resistance. Okay students, so let's start the video with the Ohm's law. Okay, so this is a very common law, Ohm's law. Let's see it very easily. According to this law, at constant temperature, okay, electric current flowing through a conductor is directly proportional to the potential difference across the ends of the conductor. Okay, and see here, the materials which obey this law, that means Ohm's law, are called ohmic or linear conductors. Na? Very simple, V is directly proportional to R. So what I am telling here, let's check here I have taken one resistance, okay, resistance R, and what is happening that here, current is flowing in this direction. How the current will flow? The current will flow because we have applied the potential difference with the help of the battery, okay. Across this terminal A and B, we have applied the potential difference. So what will happen that here? Later we will see this polarity plus, this minus. But anyhow, as of now, we have to remember that here, this potential difference, now what is this? At constant temperature, this potential difference is directly proportional to the current. Is it directly proportional to the current? So when I will remove this proportional sign, one R will come. Even I can tell here Ri, or I can tell here IR. Okay, so this is the Ohm's law. After that, if I will simplify this more, I can write here R equal to V by I. What is this? R equal to V by I. And if I will draw here V versus I graph, we can write here the slope, that means tan theta. And remember that this resistance is independent of the voltage applied and current. Okay, remember that very well. Now after that, students, if I will apply here this law, that means this side I have taken here the current, and this side I have taken here the voltage. Okay, so the ohmic conductors, they will follow what? They will follow the straight line graph, linear. Now that's why they are called which conductor? Ohmic or linear conductors. Let's take for example, this angle is the theta with the current axis. Okay, so in this situation we can write here R equal to tan theta. Okay, and here what is this? Here what is this, students? Here the temperature is constant. Okay, very very important. When the temperature is constant, it will follow the linear graph. After that, if we talk about here the SI unit and all that, okay, so okay, SI unit we will see later, no problem, but I hope so these things are very clear about the Ohm's law, and at the constant temperature all the things should be done. Okay, and the graph is the VI graph of ohmic conductor at a constant temperature. Is it great? Now after that, students, now we are seeing here the resistance. So kindly see very well. Now resistance is somewhat more detailed. So see here, resistance is the property of a material by virtue of which it opposes the flow of current through it. Again, it opposes the flow of current through it. Okay, the resistance of a conductor is directly proportional to its length and inversely proportional to its area of cross section. Okay, so let's take for example here, I have taken here one conductor like this. One conductor is there, and if I will draw here the area of cross section, so this is called area of cross section, and here I have drawn the conductor of the uniform cross section. Now everywhere the cross section is same. Now what will happen that here, if length of this conductor is L, okay, length of this conductor is L and area of cross section is A, okay, and resistivity, later we are going to see resistivity also. Okay, the resistivity of this conductor is rho. What is this? Resistivity. So according to the statement, what is this? This R is the directly proportional to the length of the conductor and inversely proportional to the area of cross section of the conductor. Okay, so after that, when I will remove the proportional sign, this will be rho L by A. What is this? R equal to rho L by A, where rho is called the resistivity of the material, or even we can tell specific resistance also. We will study in a detail, not a problem. Okay, but remember that here R equal to rho L by A for a given conductor. After that, if I will talk about here the SI unit, what is this? SI unit of the resistance. So you know R equal to V by I. So even I can write here volt per ampere, or one more is there, ohm. Ohm, the symbol is this. Okay. After that, if I write here the dimensional formula of the resistance. So to calculate the dimensional formula of the resistance, we should know the some formulas. Like even you can use this also, like R equal to V by I. From here you can get, or you can get here with H equal to I square RT. I hope so you know this Joule's law of heating very well. So, but I will calculate from here. So what will happen that here? This R will become here H by I square T. Okay, what is the H? H is the heat, that means I can write here ml square T power minus 2, just like energy, because heat is a form of energy. Current means A square and the time is T. Okay, so see, very easily we have got here ml square T power minus 3 A power minus 2. Kindly see, very well. Is it? So here we have seen this resistance R equal to rho L by A, SI unit and dimensional formula. And remember that here, it is looking like R equal to V by A. See here please, it is looking like R equal to V by I, but R is independent of the V and E. Then R depends upon which factors? R depends upon the resistivity of the material, length of the conductor, length of the material, or even we can tell area of cross section. Depend on these things, but independent of voltage and current. Is it, students? I hope so you have understood very well what I am coming to tell you. Okay, great. Next one we are going to see in our detail resistivity or specific resistance. As I have told you, this is called the rho. Okay, so see here, resistivity is the intrinsic property of a material. Which property? Intrinsic property of material. It is independent of shape and size of the material and depends on nature and temperature of the material. Very, very important. Nature and temperature of the material. Okay. And even in our previous videos and all, you have seen that here. This resistivity is given by rho equal to m by n square tau. What is this here? Rho is given by m by n square tau for a material, where m is the mass of the, for conductor I am telling now, m is the mass of the electron, n is the number of electrons per unit volume, E is the electronic charge, and tau is the water. The tau is the relaxation time here. Kindly see here. Very well. If I write here the SI unit of the resistivity. Okay. So for the SI unit, what I will do here, for the SI unit, I will use this formula. You know, R equal to rho L by A. Okay. So from here, I can write here rho equal to R A by L. Okay. And R means ohm, A means area of cross section, meter square, and length means meter. Okay. So when you will simplify this, what this will happen here, students, it will become here the ohm meter. What is this? SI unit is the ohm meter. Okay. After that, students, if we will go for the next one, let's check dimensional formula. Dimensional formula. So what we have to do here, in a resistance dimensional formula, we have to just multiply with the L. Okay. So what this will become here? Before that it was ml square, now it will become ml cube T power minus 3A power minus 2. Kindly check out very well. This L square will become what? This L square will become here L cube. Okay. So ml cube T power minus 3A power minus 2. And remember that here, this resistivity is independent of shape and size of the material, only depends upon the nature and the temperature of the material. Okay, very important. Next, students, here, if we talk about here the conductance. So conductance here, it is the reciprocal of the resistance of a material. Mathematically, what is there? I can write here, this conductance means G. So G is given by here 1 by R. You know, R equal to V by I. So even I can write here I by V. What is this? I by V. And if I draw here one graph, now I am going to draw here the I versus V graph. Which graph? I versus V graph. And let's take here for the ohmic conductor, what will be this? This will be the straight line, is it? So let's take for example, if this angle is alpha. Now angle from the voltage axis, how much? Alpha. Now this V is the volt, I na ampere and all. I think this is very clear. So what will happen that here, this G is given by tan alpha. What is this? This conductance is given by what? G equal to tan alpha. Now kindly see here, tan alpha. Now, G is given by what? Tan alpha. And one more thing, if in case sometimes I versus V graph is given and they are asking the resistance, then you will see the angle from here. This angle will be theta, and even you can write here R equal to tan theta also. Okay, R equal to tan theta. And if in case, if we go for the somewhat back side, see here I have taught you, V versus I graph is given, and they are asking the conductance. So here you will make this angle alpha, and directly you can write here G equal to tan alpha. So what I am telling you, for resistance, see the angle from the current, and for the conductance, see the angle from the voltage. Is it? I hope so. Very, very clear. Okay. After that, we are going to see for the SI unit. Okay. So SI unit. SI unit of the conductance is what? Ohm inverse. No? Ohm inverse, or we can write here the mho. No? Ohm inverse or mho. After that, if I talk about here the dimensional formula, okay. So first I will write here the dimensional formula of the resistance here, okay. So what is this? We have seen that, students, ml square t power minus 3 a power, what was there? Just go for this one, because I don't used to remember, na? A power minus 2, is it? Ml square t power minus 3 and a power minus 2. This is for the resistance. Now if we want to write for the conductance, you know what will happen there? It will just become reverse. M power minus 1, no? L power minus 2, t power 3 and a square. Okay, this help I have taken. Okay, just I have made it a reverse. Kindly see, very well. We are seeing here the conductance. Is it? Great. Now students, now let's move for the conductivity. Like resistivity, na, in the same way conductivity. But let's see. Conductivity is also the intrinsic property of a material. It is independent of shape and size of the material and depends on nature and temperature of the material. Na? Independent of shape and size, depends upon the nature and the temperature of the material. Now see here, it is the reciprocal of the resistivity of the material. Okay, so mathematically if I write here, I can write here sigma equal to how much? Sigma equal to 1 by rho. Okay, and you know rho equal to m by n square tau, so it will become here what is here? Ne square tau by m. This is called here the conductivity. Okay, and if I write here the SI unit of the conductivity, you know for the resistivity is the ohm meter. So here what will become here? Even we can write here, see, even I can write here ohm inverse and meter inverse, or we can write here mho, na, OHM MHO. So mho per meter, both are there. Okay, mho per meter. After that, if I write here the dimensional formula of the conductivity. So if I write for the resistivity dimensional formula, what was there? It was there ml cube t power minus 3 a power minus 2. This time I remember, is it? So now the dimensional formula of the conductivity will become what here? Make it reverse, m power minus 1, l power minus 3, t power 3 and a square. This will be the dimensional formula of the conductivity. They may ask in an exam. So kindly see very well. Now we are seeing here the conductivity. Is it? Great. Next one is, students, we are going to see here the effect of temperature on resistivity. Okay, so students, we know that rho equal to m by ne square tau. Okay, m by ne square tau. Okay, so see here the first one, the resistivity of conductor is directly proportional to its temperature. Very, very important. Because with increase of temperature, its relaxation time tau decreases, but number density n remains constant. Number density means number of electrons per unit volume. So mathematically what is happening here? Remember that here for the conductor rho is the directly proportional to temperature. Okay, and why this is happening here? Because you know very well rho is the directly proportional. You see m is constant, n is constant, E is constant. So we can tell here rho is the inversely proportional to tau. Okay, and what will happen that here? When the temperature will increase, the electrons will move more faster, the time between two collisions will decrease. So that time what will happen that here? This tau will decrease and this resistivity will increase. Even reverse also true. What is the reverse true, students? If the temperature is decreasing, this now the electrons will move slowly, tau will increase. Okay, and the resistivity will decrease there. Now please remember that all these things. Okay, this thing we have done it here, is it? Now remember that here, see, temperature coefficient of resistance, that means alpha, for a conductor is what? For a conductor, the temperature coefficient of resistance is positive. Okay, that means with increase of temperature, resistivity and resistance will increase. Okay, great. Next one, second one, we are going to see, students, can you see here? Resistivity of semiconductor is inversely proportional to its temperature, inversely proportional to its temperature, because with increase of temperature, its relaxation time tau decreases and number density n increases. But number density dominates over relaxation time. That means at the end the number density will decide what is going to happen. So according to the statement, what is happening that here, this resistivity is what for the semiconductor, rho is inversely proportional to temperature. Okay, and if I write here from the formula, rho equal to m by n square tau, so I can write here rho is the directly proportional to n into tau, n into tau. Okay, who will decide here? Here this n will decide. So what will happen that here, if in case when we are increasing the temperature, so with the increase of temperature, what will happen that here, this tau will decrease, okay, n will increase, tau will decrease, n will increase. But who is the deciding factor? N is the deciding factor. That means the what n will tell, that will happen. What n will tell, that will happen. Okay, that means anyhow what will happen that here as n is increasing, this rho will decrease here. Okay, so what will happen that here, this rho is decreasing here. Even with the decrease of the temperature also same thing will happen. Temperature decrease, this tau will increase, n will decrease. So anyhow this resistivity will increase here. Is it, students? Kindly see very well. Okay, and after that, if we talk about here even the graph also, so here please, for this graph for semiconductor, na, this rho, this is the temperature, inversely proportional, na, just like a rectangular hyperbola. Okay, and if I draw here, now so here please, this is the rho and this is the temperature. Here it will be the like a straight line, like this it used to be there. Okay, even it can pass through the origin also, no problem, but ideally the materials don't follow like this here. Okay, let me draw here and let me draw here the dotted line here, that is the better. Okay, so kindly see very well, we have seen here the resistivity and all that. Okay, great, all these things we have seen here. Next one, students, is there, see here. See the resistivity formula with the temperature. So see here, the resistivity of a material is found to be dependent on the temperature over a limited range of temperatures, not all the temperatures, only over a limited range of temperatures. Okay, students, so what will happen that here, the resistivity of any material is approximately given by, I will write here, but first here, where rho T and rho naught is the resistivity of the material at temperature T and reference temperature T naught respectively. So rho naught at temperature T naught, rho T at temperature T. So I can write here, this is given by rho T equal to rho naught and here 1 plus alpha T minus T naught. Okay, this graph will be, means this formula will be valid. If both the sides I multiply with the L by A, then this will become here RT equal to R naught 1 plus alpha and here T minus T naught. Okay, kindly remember this formula. And whenever the numerical is coming, okay, one more formula used to be there like this one here, see, RT2 equal to RT1 1 plus alpha T2 minus T1. Okay, but remember that here most of the time this is the approximate formula, na? So this formula we will not use here. Which formula will use here? Which formula will use here? First we'll write here the RT2 like this, R naught 1 plus alpha T2 minus T naught. Then we will write here RT1 means R naught 1 plus alpha T1 minus T naught. And what we'll do? We will divide this equation and then we'll get the answer here. Okay, so by dividing the equation and all, we'll get here this equation we will use, this equation we will avoid, na, because this is the approximate formula. Okay, is it great? Now students, next one we are going to move for this one here. What is this? Resistivity versus temperature graph for the copper. Okay, so what will happen that here, if this side this is the temperature, this side this is the resistivity, this is by default Kelvin also, and here the rho means anyhow ohm meter. Now I am writing here the SI unit. So what will happen that here, for the copper the graph used to be like this, little bit like this, little bit curved. Okay, for nichrome, if I draw here the nichrome is the one kind of alloy. Okay, so here also this resistivity is there, na, SI unit anyhow, again and again writing here, ohm meter and temperature Kelvin. So what will happen, the graph will go like this is there for the nichrome, na, kindly see very well, for copper and nichrome. Is it great? Next one, students, here for semiconductor, as semiconductor is we have seen also which are the elements are there. Silicon is there, Si, what is this? Si, and germanium. Silicon means atomic number 14, germanium means 32. Okay, and in their outer shell they will have the 4 electrons. Okay, and if I draw here the graph here, let's take for example, this is the temperature, this is the resistivity. So like this graph will be there. Why? Because we have learned rho is the inversely proportional to the temperature rectangular hyperbola. Which shape? Rectangular hyperbola. Next one is, students, for constantan or magnet. This is also one of the alloy, very important, used in the potentiometer, wire, tungsten bridge and all that. Alpha, temperature, coefficient, resistance will be nearly 0. That means what will happen that here, their resistivity and temperature graph, what I am telling, their resistivity and temperature graph will be nearly independent of the temperature, nearly independent of the temperature is there. Okay, so remember the students, all these kinds of graph and all that for semiconductors and constantan or magnet, very important alloy, alpha is nearly 0. Okay, next one, see limitations of Ohm's law. Now, because Ohm's law is not a fundamental law. Ohmic conductors will follow the Ohm's law, but lot of materials, electronic devices are there and they will not follow the Ohm's law. Okay, so kindly see here, Ohm's law is not a fundamental law of nature, because see the first one, conductors obey Ohm's law at lower values of current, because at lower values of current the heat dissipation from the Joule's law of heating will be very small, so we can consider temperature is constant. But when the current will increase, the temperature will increase, so that time it will deviate from the Ohm's law. So say here, but deviate from it at higher value of current. That means low value of current we can consider nearly temperature is constant, but higher value of current we can't avoid this. Okay, so what will happen that here, if I draw here the graph here, see this is the V, this is the I. So normally what will happen that here, if I draw here, normally what will happen that here, see ohmic conductor will go like this, but in case of normal conductor means at lower current and all they will go, now lower value of current, directly proportional. But if you go for the higher value of current, what will happen that here, they will deviate. That means it will go like this dotted line will be there. Okay, like this, remember that here. Okay, it will deviate from here. And to be more specific, what we can do, even we can rough this also, so that you should not get confused here. Okay, great. Can you see? Very well. Now this is the first limitation, lower value of current following, higher value of current it is not following. Okay, in a practical situation. Second one, what is happening that here? Kindly see very well. Second one. So second one, what is there? See second one, non-ohmic elements like vacuum tubes, PN diodes, transistors and electrolytes does not follow Ohm's law, because they show different current values for the positive and negative value of potential. What is the meaning of this? If somewhat you have studied about the PN diode, so let's take for example, this is the current, this is the voltage, this side positive voltage and this side negative voltage. So what will happen that here, students, here see, in first quadrant the diode will be forward bias. Forward based diode means will apply like this is there. Okay, like this, this is the plus, this is the minus, forward bias. So what will happen that here, the graph used to be like this. And after that what will happen that here, students, here, if I make the diode reverse bias, that means this side positive and this side negative, then what will happen that here, now the graph will go like this is there, and here the current will be microampere. So you can see very well in forward bias and reverse bias the diode is behaving differently. Okay, that's why it is not following the Ohm's law. This is the forward bias, reverse bias. If we talk about here the actual conductor, so you know what will happen that here, let's take this is the voltage and this is the current is there. Okay, current minus I, and here voltage minus V. So you know, students, what will happen that here in this situation, it will just, if V is positive, I will be positive, that means like this here. If this is plus, this is minus, the current will flow in this direction. But if in case I make here the reverse, this plus, this minus, current will flow in a reverse direction without any problem and all that. That's why this is called here the bilateral device. Like that it will go here. Okay, so that's why this is called the bilateral device, and this is called here the unilateral. Now, because in a forward bias and reverse bias it is behaving differently. Is it, students? I hope so. This is very clear here. I versus V graph is there. Remember that here. Next, students, 13th one, see. Materials like gallium arsenide does not obey Ohm's law, because there is more than one values of V for the same current is there, for same current I. Okay, so what I am doing here, let's say here for example I am drawing here the graph here. Okay, this is the current most of the time in a milliampere, and this is the voltage volt. So you know what kind of graph this kind of material they used to show now. First what will happen that they will follow the straight line. Okay, after that what will happen, they will get a little bit curved, then it will go like this, and like this it will happen that here. Okay, so what will happen that here, students? Up to this they are following the Ohm's law, but after that what is happening that here, students? Here in this region, if I write here the O, A, B, C, D. Okay, so this is a non-linear region. A to B is called which region, students? Non-linear region. And here A to B, what is this? Students, very important, this A to B resistance is positive. A to B resistance is positive, slope. But if I talk about here in this situation, B to C, what will be there? The resistance will be negative. Okay, and after the students, even if I draw here the one line also, see, you can see here. See here, this. See, if I draw here like this here, so you can see, students, here, no? Different values are possible here. See, for the different voltages, we are getting the different. No? See here, the voltage is getting different, but the current is same. Okay, that's why they are also not following the Ohm's law here. Kindly see very well, the gallium arsenide is there. Okay, great. Now, students, if we'll see, talk about here the VI graph. Which graph? VI graph used to come in exam. So see here, please. VI graph at different temperatures. So what is happening that here? See here, students. This is the V. This is the I. Okay, and if I draw here the graph, let's take for example this one and this one. This is at temperature T1, this is at temperature T2. Then you know what will happen at here. Let's take this angle θ1 and this angle θ2. Is it? So I have taught you very well, R equal to V by I is equal to tan theta. Is it? So you know very well, the resistance where slope is more, θ2 is more than θ1. So R2 is greater than R1. But you know, in case of conductors, what is there? The resistance is directly proportional to temperature. Okay, that means what will happen that here? The temperature T2 is greater than T1. Now, more resistance, more temperature. Is it? Great. Next one, if we talk about here the IV graph at different temperatures. Okay, anyhow, see. Let's take here, this is the I, this is the V, okay, and going like this is the, I have drawn here like this is there, okay, and let's take, I have taken some temperature is there, students. Let's take T3, and here I have taken here T4, okay. So in a shortcut way, what I will do here, I will see the angles from here. Now I will see from the angle point of view, θ1, θ2. So where angle is more, T3 angle is more. That means I can tell here very easily, students, this T3 is greater than T4. What is this? The temperature T3 is greater than T4, everything most of the time in a Kelvin. Okay, great. Some important points is there. Let's see one by one some important points, students, here. Na? Very, very important. Can you see here? Because question used to come from here. So see here. Generally, resistivity of alloy is more than resistivity of semiconductor is more than conductor. Now, so please remember that here resistivity of the alloy is the maximum, conductor is the minimum. Second one, what is there? See, the temperature coefficient of resistance of a semiconductor. We have learned this. Carbon means graphite, insulator and electrolyte is a negative. That means with increase of temperature, resistivity will decrease. Okay. Third one, students, here. The heating element devices like a heater, geyser, electronic iron we use in our home, pressure, are made of nichrome. Remember that, are made of nichrome. It has high resistivity and high melting point. Now, made up of nichrome, high resistivity, high melting point is there. Okay, great. Next one, can you see here, students? Fourth one, important. Fuse wire is made of tin lead alloy because it has low melting point and high resistivity. The fuse is used in series with appliance to protect it, because what happens sometimes, even you will observe also, sometimes appliance is working and suddenly it will get cut off. Then we have to go down and we have to again replace the fuse wire. So fuse is just a device to protect the device element. And remember that here there is the fuse rule is there, or we can tell fuse law is there. And what is this? This I square is directly proportional to the D cube. What is the D? D is the diameter of the wire. Okay, if in case this is the wire, fuse wire. Okay, so what is this? This D is the diameter of the wire, and I is the current flow through the wire. So I square directly proportional to the D cube. Fifth one, students, see, the resistance of resistance box are made of Manganin or constantan alloy. As I have told you, alpha is nearly 0 because they have moderate resistivity and very small temperature coefficient of resistance. That means alpha nearly 0. See here, the resistivity is nearly independent of temperature, as I have drawn here before the graph also. How the graph was there, students? See, this was the rho and this was the temperature. It was nearly constant. Is it? Kindly see it. Okay, great. Now, students, kindly see here. The sixth one, what is the sixth one is there? See, the filament of bulb is made up of tungsten, because it has low resistivity and high melting point. The bulb is filled with the inert gases, like a neon, argon is there, because at a high temperature, tungsten reacts with air forming a oxide. Remember that here, made up of tungsten. And the last one, the connecting wires are made of copper, because it has low resistivity. Kindly see very well. So students, I hope so this video of the Ohm's law and all these applications, temperature dependence and all, you have studied very well students. Keep studying, keep growing.